Homework 29, page 478. This is section 7.8. We're doing 9, 11, 15, 19, 27, 29, 31, 37, 47, 53, 55, 57, 59, 63, and 65. Now, what's this limit?
Well, we can't just plug in
Yeah, right. What happens if you do just plug in a 1?
blows up.
Yeah, we could see that blows up. What's log of 1?
0.
0.
So it's 0 over
So
0.
it's 0 over 0. So I'm not gonna don't. This is it's not equal to, but you get the idea. This is going to 0 over 0. Have we seen limits that go to 0 over 0 before?
Yeah. Like. Wait.
What I'm thinking in particular is the difference quotient.
Yeah.
Now, remember, this is one way of writing the difference quotient, right? Like, we could do f of x plus h minus something, or we could think about it like this. As x goes to a, right? And we can see that this, in fact, every difference quotient goes to 0 over 0, right? Like, if it doesn't, then it's not a difference quotient, because by the very way it's set up, right? We have some function, you have some a, you have some x, or you have an x and an x plus h, whatever, right? It's the same thing. And what happens is, like, as one moves to the other, as one input moves to the other input, right? The rise and the run both go to 0. And so the slope, right, or yeah, the rise goes to 0, the run goes to 0, but we've seen that this could be really anything, right? Yeah. It might be the case that it's infinite, it might be the case that it's 0, it might be negative infinity, or it could be any real number in between. So this really doesn't tell us much of anything, right? But it's not so alien that we're completely in the dark. We've seen this before, right? A limit of something going to 0 over 0 usually have to do some kind of finagling to make it work, right? And figure out what's going on. Any ideas on how to finagle? Because what we've done before is we've had something like this, x plus h squared minus, I don't know, 5. And then we have an h down here, and hopefully you could do, or actually, that wouldn't do it. It would have to be minus x squared. Right, we do something like this, and then we factor out an h, and then blah, 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 blah. Yeah. What do you think we could do with this guy to make that go away?
Substitution.
Maybe. You could try that. Like, let u equal x minus 1. And then we'd have, in the top, we'd have u plus 1. Still have problems. What if we did this? What if we had this limit? And let's just look at it real quick.
Oh, you can just plug in values up to like 0.9.
That's what we're going to do. That's what we're going to do. But what about this? This goes to, again, 0 over 0.
Yeah, so it equals 1 or something.
It does equal 1. And remember what we had to do to get there. When we we had to do some crazy stuff with triangles and all kinds of things, and then figure out blah, 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 blah. And that's one way we could deal with something like this. Another way we could deal with something like this is to say, this is x minus x cubed over 3 factorial plus x to the 5th over and then that's divided by that, so that's the same thing as the limit of 1 minus x squared over 3 plus x to the 5th over 5 factorial, these are all factorials, and then say, well, the limit as x goes to 0, there's no problem there, that guy goes away, and it's just 1, which is what we found the hard way. So what we could do in this case is find the Taylor series for this guy. And it would make sense to find the Taylor series evaluated at 1, or at where x0 is 1, And it works out to be something, I don't know, I don't really care if it's x minus 1 squared and some stuff and blah blah blah. And it turns out that the x minus 1 would cancel all of these guys and blah blah blah. But there's an easier way. There's in fact a much easier way. What I'm about to do is not the way. But let's investigate this thing, okay? So we have some function, log x. It looks like this. And here at 1, it goes through 0. We have another function, x minus 1. This happens to be the tangent line here. It happens to be the case that this is the tangent. In fact, if you were to go y equals mx plus b, and then say that m has to agree here, we'd say m has to be the same thing as f prime at 1. F prime, thinking of f as log x, then f prime is what? 1 over x. And so f prime at 1 is 1 over 1, or just 1. So we get y equals 1 x plus b. And we know that when we plug in a 1, we got to get out of 0. So I plug in a 1, get out of 0. B is negative 1. And so the line, the tangent line, happens to be x minus 1. So it happens to be the case. Okay, all right, keep that in mind. So, okay, what we could do is, like you're saying, we start plugging in values that are really close. And if you did that, you would notice, and like if you were to zoom in on this picture right here, right? Because it's the tangent line, right? This guy looks a little less curved, and they hug a lot longer, right? Zoom in some more into here, and eventually there's not going to be any difference. He's going to look like a line, and this guy's going to be dead on top of him, right? And so we could do the thing where we plug in values that are really close. And if you do that, right, you could say, well, since log of, say, 1.0001, and we could go 1.0001 minus 1, and we get some value that's really close right here, and we'd see that this is, and you could plug that into your calculator, and you would get that it's approximately 0.0001, and 1.0001 minus 1 is 0.0001, and we can see that this does go to about 1. Okay? And so we would guess this looks like 1. Okay. Okay. Does that convince you that this is that the limit of this is probably 1? Yeah. Okay. Now, but what if it weren't the tangent line? What if it were something different? What if it's still x goes to 1? We still have log x. And what if we had something that also goes through at the same point, but it's not tangent to it? So let's say 2x minus 2. So we have log x, which does this. It goes through here at 1. But now 2x minus 2, it happens to go through the same point, but its slope is steeper. In fact, I'm going to do it like this, and he's going to come down like that. It's really bad. It goes through at minus 2. Well, we could do the same kind of thing. We could zoom in right here. And what we'd see if we did zoom in is that the slope of this guy, the slope of log, looks about like 1. And when we zoom in really far, he looks just like a line. But this line, 2x minus 2, is a line, and when you zoom in on it, it always looks like this. It always has a slope of 2. No matter how far you zoom in, it's going to look more and more like a line. And this one is always going to be 2 times whatever that one is. So for instance, then we go and we plug in some values that are really close, right? Like we point in 1.0001. And we'd find that log of 1.0001 is really close to 0.0001. And then 2 times 1.0001 minus 2 is 2.0002 minus 2. It's 2 times whatever this was, right? 0.0002. And yeah, and so it does make sense, right? Because this guy, as we get closer and closer to the value that we're going to, x minus 1, this guy is always 2 times whatever this is. If that happens to be 0.03, this guy's going to be 0.07. Yeah, it's just, that's kind of how that always works, right? He's always, if this guy is almost like a line, and this guy is a line, but he's just 2 times, right? The slope is 2 times as much. Then he's always going to be 2 times. It's always going to be 2 times that. He's in the bottom, and so this is going to get closer and closer to 1/2. I'm going to guess that the limit here is 1/2.
You could even factor out it too.
You could factor out it too. You could factor, exactly, right? Just like we did before, right? It's not going to help. And then another thing you could have done is expanded log x as a Taylor series, f prime, f double prime, because the first one was 0. You could mess with this one, who cares? X minus 1 squared. And then in the denominator, you could, like you said, factor out your 2. And these guys will all cancel. You'll be left with a 1 right there, and a 2 down here, and you'll have 1/2. That doesn't help us much if the limit were, say, something like that. Or how about minus 1? Because you're not factoring out an x squared. Or what if it were like the 9th root of x squared? You're not factoring that out of anything. It turns out there's a better way. There's a better and easier, way easier way of dealing with these. That's not some stupid geometric argument. Because I set this up so that there was a nice geometric argument, but what we're going to see are the ones that we're going to deal with today. There's no way. You just, like, aside from, well, it looks bigger, by how much, I don't know. You're not going to get anywhere with a geometric argument. Also, a Taylor series, what's nice about what we're about to do is it will work with things that don't have Taylor series. It will work for functions that don't necessarily have a Taylor series. Though, what are those? But don't worry about that, right? Every function that we care about, that you will ever deal with, has a Taylor series. But we don't want to have to compute the Taylor series every single time we're trying to do something like this. And like we just saw, what if your denominator is something that's not conducive to that, right? Like, you're not factoring anything out of that. Like, sorry, that's just not going to work. This happens to work. So, this is where we're going. We have this really cool fact. It turns out that if the limit as x goes to some number a, and a might be plus or minus infinity. Okay? Here we happen to be going to a number, but what I'm about to write works whether the limit's going to infinity, negative infinity, some number, doesn't matter. If the limit of f of x over g of x, as it goes to some number, goes to 0 over 0, then this limit that we're trying to figure out, the limit as x goes to a of f of x over g of x is equal to, drum roll please, nope, because was it 1 there? No. And that goes to 0 over 0. And like we said, with a derivative, it could be any number. What it goes to, if you notice what we did here, we had this guy, and let's say in the second case we had this guy. It had something to do with the slope, right? As we were looking at it, we were kind of saying, yeah, the slope is the same as the slope of this guy there, right? The slope was 1, the slope of that guy was 1, and so they went down, they went to the same place at the same speed. This guy, the slope was 1. The bottom guy, the slope was 2, so he went down 2 times as fast, and that's why he kind of got to the place 2 times faster, right? So what it is the limit of the derivatives, g prime. Now notice, this is not the same thing as you take the f over g and take its derivative, because that's f prime g minus f g prime over g squared. This does not say that. What we're doing is we're comparing the ratio of the derivatives of the functions themselves.
Yeah.
Okay? So let's just do that. Let's just do that here and see if that works. This tells me, if this is true, which we haven't proved, if this is true, then this should be the same thing as the limit as x goes to 1 of, what's the derivative of log? 1 over x. What's the derivative of that? Over just plain old 1. Which is the same thing as the limit as x goes to 1 over of 1 over x, which is just what?
1.
Ah, it works. Let's try it here. This should be the same thing as, and because it goes to 0 over 0, right? And you'll see this is important. It has to do this, otherwise it ain't gonna work. But because I look at it, it goes, it looks like it's approaching 0 over 0, then this tells me that as I do this, it should be the same as, okay, so what's the derivative of the top?
1 over x over 2.
Over 2. So again, we're comparing the derivatives. This says just compare the slopes. The slope as this one goes to 1 looks like this. The slope as this one goes to 1 is this, and we get 1 over 1 is 1, over 2 is just 2, and hey, there you go. Okay? So, I would like to prove this, but I'm not going to. What I'm going to do, now this, by the way, well, actually, just hold up. So what I'm going to do is not a proof. Normally I would write theorem, and then I'd have the statement, and then I would write proof. I'm writing not a proof, because this is not a proof. The actual proof, if you're interested, you could go to, I would suggest go to Wikipedia and just type in what I'm about to write what this is called in a minute. Just bear with my insanity. Look it up, and you can see a proof for it, and you'll see why we're not doing it. It's actually quite involved, and the way the book does it, I don't like. And I'll show you why I don't like it in a minute. The book does it twice. The first time I hate. The second time is good for this case. And don't worry about that timer. My wife should come and hopefully she hears it. I hope it doesn't drive you crazy. Oh, there she is. Okay, so the second proof the book gives is, again, quite involved, and it will take us a long time to really dig into it. And so you could look at that, but again, that itself is still incomplete. In order to do it the right way, look at Wikipedia and you'll see, oh, that's why we're not doing it. It's quite involved. But what I'm going to do, instead of giving you a proof, I'm going to give you an idea of why it works. And what I'm going to write up here is how they prove it, though what I'm going to do is not rigorous, and I'll show you why it's not rigorous here in a minute. So assume that this is true. Okay, so if this is true, if the limit goes to something over, it goes to 0 over 0, right? So if the limit as x goes to a of f of x over g of x approaches 0 over 0, then we could say that f of a is 0 and g of a is 0. We're assuming that these are differentiable functions. If they're differentiable, then they're continuous, which means they don't have any jumps. So if this is approaching 0 as you go to a, then it's actually a, right? Right? That's all that means. As you go to a, you get out an f of a, like that. And we're assuming implicitly, I didn't say at the very beginning if f and g are both differentiable, but that right there tells you, well, they gotta be differentiable if you're doing that. And so if they're differentiable, they're continuous. If they're continuous, then as you approach A, and it goes to that, you get the same thing as when you actually plug it in. There's not any holes, because then this guy would no longer be differentiable, would he? Right? So, okay. So that's all I'm saying here. That's just a fact. F of A and G of A must both be 0. And we saw that earlier, right? Log x as it goes to 1 goes to 0, and indeed log of 1 is 0, right? So that's all I'm saying right there. Okay, so if that's true, then let's look at this actual limit. Limit as x goes to A of f of x over g of x. Well, that's the same thing as this. As x goes to A of f of x minus f of A over g of x minus g of A. Why? Because that's just 0, right? And that's just 0, right? So really, I'm just saying this is equal to that. And since they both happen to be 0, we can do that nifty little trick. Okay. But this is the same thing as this. Do you believe that?
Yeah.
Okay. And then that's the same thing as this. And so that's the same thing as this. Limit as x goes to A, f of x minus f of A over x minus A, all over g of x minus g of A, A, x minus A. Yeah? And that's the same thing as this. Right?
Yeah.
Right? But that's just the derivative at A, right?
Yeah.
Right? Like that's just f prime at A. And that's just g prime at A. Right? And let's just make sure here. Here's f. Here's A. Here's x. Here's f. And so f of x, f of A. This quotient is just the slope of that line right there. And as x goes to A, this guy gets closer and closer and closer. And so what we'll end up with is the slope of the tangent line at A, which is the derivative of f at A. Ditto with g, right? So I'm going to rewrite that. That's the same thing as f prime of A over g prime of A, which is the same thing as the limit as x goes to A of f prime of x over g prime of x, right? Assuming the derivatives are continuous. I didn't write that up there. But if the derivatives are continuous, you get that. And I think in general with this, they might not need to be. I could be wrong about that. I'd have to look again at the proof.
Well, the derivative's continuous and isn't the other. Is the original function continuous as well?
The derivative can be discontinuous, so with a continuous function. So if that's the derivative, so it jumps from 1 down to -1.
Oh, then it just stays.
But what
Yeah,
it does
has
is it has a corner then, right? Then the original f, so if this is f prime, it jumps. The original function is continuous, but it's not differentiable right there, where the jump is here at, say, A. So I'm not quite sure. Again, it's a bit advanced for our class, the actual proof of this. But this gives you an idea of why it's true. Okay, so we saw that we saw by graphically that, yeah, if you're trying to figure out if two things are going to 0, it depends how fast they're going to 0. If one's going twice as fast, then he's going to end up with a 2 there, right? Right? Like he's always 2 times as much or less than the other one, right? And so it makes sense that you, in order to find if a function if the ratio of two functions is going to 0 over 0, then it matters how fast they're getting there, and that's what this is. Now we've seen a proofy thing here. You see what I don't like about this though, and why I think this isn't quite as rigorous as I'd like, is if this is going to 0 over 0, I could literally choose any function that goes to 0. I could say, well, if this goes to 0 over 0, then that's the same thing as a limit of, I don't know, e to the x plus a, and let's say it's going, I don't know, it's going to 0. I could say this is the same thing as e to the 5 plus x minus e to the 5. And that's the same, gee, wow, how about 5 plus x minus log 5? And that's, so this, I don't know, this step right here bugs me. I don't like it. It's not quite rigorous because, well, why don't you just do that? The actual proof takes care of that. It does, the actual proof does it really well. But does this suggest to you that this is probably true?
Yeah.
Okay, all right. So it's not a proof. It's not a proof, but I think we have enough to go with here. And this is called anybody guess how you pronounce this? L'Hopital's rule. Okay, so L'Hopital's rule. But there's more. It's not just if it goes to 0 over 0. It also works if it goes to infinity over infinity. So if you have a function that goes to infinity over infinity, and it could be plus or minus, so it could be going to negative infinity over positive infinity, or positive infinity over positive infinity, or positive over negative, or negative over negative, who cares? If there are two infinities there, then this still works. Because again, you're asking, well, how fast is this one going to infinity? And how fast is this one going to infinity? You know, whatever. That's what you're asking. You're basically saying who gets there first, in a sense. That's what this means, right? How fast are you going, right? That's what the derivative of the function is. Okay. Now, note, this does not work if you don't get 0 over 0 or infinity over infinity. For instance, the limit as x goes to 0 of sine x over x plus 1. Does that go to 0 over 0?
No.
What does it go to?
0 over 1.
0 over 1, which is?
0. It's
just 0. But if you just blindly applied L'Hopital's rule to any limit you find, you can say, oh, I'm going to use L'Hopital's rule. And so, this is the same thing as the limit as x goes to 0. What's the derivative of sine?
cosine
Over 1. And now that would be cosine 0, which is 1. That's not true, right? You have to have this for it to work, okay? Check it every single time, because your book will mess with you. It will give you one that doesn't go to 0 over 0. You're like, oh, I'm in the section about L'Hopital's rule. It must do L'Hopital's rule, so you just blindly do it. No, not necessarily. Just chill out. Here's another example. Look at this. Limit as x goes to 0 from the right of log x over sine x. What does this go to?
0 over 0. Wait, no, this.
What's log go to?
Infinity. It's negative infinity.
Negative infinity, right? Because log does this, and as you go to 0, he goes to negative infinity, and sine goes to 0. What's that?
I have no idea.
Well, think about it this way. If you had 5 over 0, this would go to, you would say that this limit
Doesn't exist.
doesn't exist because it would blow up, right?
Yeah.
You'd say as this gets really, really, really small, the entire thing gets really, really, really big. And if it's negative, I guess it would be blowing down to negative infinity. Who cares? It's going to infinity. You'd say it does not exist. Same thing here. He's just getting there even faster now, right? He's going off to negative infinity. The denominator's getting bigger, so he's still going to be going off to negative infinity. So you'd say it does not exist. Okay? So careful with that. Now, what if we had done it the other way around?
0.
Yeah, so if we had sine over log, you'd say, well, he's going to 0 over negative infinity. What's that?
0.
0.
Oh.
Right? Because if you had any number, 700, over something that goes to negative infinity, you'd say, well, this is going to get really, really, really small. It's going to go to 0. And so 0, well, yeah, he's still at 0.
So 0.
So we
Trumps
should see 0.
infinity. 0 trumps infinity.
In this case,
So 0 times infinity.
we'll get there. We'll get there. We'll get there. It depends. I remember in Algebra 2, somebody asked me, what's 0 times infinity? It depends. It depends. You'll see. Stick around, you'll see. So, okay, we have not a proof of L'Hopital's rule. Okay? In order for L'Hopital's rule, you have to go to 0 over 0 or infinity over infinity. Here's an example of one that goes to infinity over infinity. Limit as x goes to infinity of x squared over e to the x. What does it go to? I just told you. Infinity over infinity. So we can apply L'Hopital's rule. And what I do whenever I go to apply L'Hopital's rule, now first I checked it, right? I'm not writing it down, but I am checking because if it doesn't go to either this or that, then you can't continue, okay? We just saw that like 2 times, like 3 times. It's not going to work. But I checked. That goes to infinity, that goes to infinity, and so I can use L'Hopital's rule. And so what I do that so that whoever's grading my paper or whoever's trying to follow along understands what I'm about to do. You don't have to do, I mean, it would be really cool if you did. And it's not quite standard, but anybody who knows what we're talking about here would go, oh, L'Hopital, I like that, you know? And that's the idea, right? Like, you're trying to communicate. I want to be clear. I'm applying L'Hopital's rule right here. Okay, so, what over what?
2x over e.
2x over, he hasn't changed, just plain old e to the x. Okay, so what's that?
Well, it also goes to.
It still goes to infinity.
Do it again.
Use it again, and you could do that. But you got to make sure he's going to infinity over infinity, still. Now there will be times, though, and you'll see soon, that if you just take a second and see, does anything cancel out? In this case, no, nothing does. Okay?
Oh, yeah.
Right? Because we'll see in a minute, like, or maybe you could rearrange it so that you could actually evaluate the limit. But if you just blindly go, very often, you'll just keep going forever. It's just, well, it's still 0 over 0, L'Hopital's rule, still 0 over 0, L'Hopital's rule, still, there you go, right? Or something like that. And you could just keep going forever. Stop and think, wait, no, okay, yeah, he's still going to infinity, he's still going to infinity. Nobody's canceling anybody here, so I'm going to apply L'Hopital's rule again, and that gives me the limit as x goes to infinity of what?
2 over e to the x.
2 over e to the x, which is what?
0.
Yep, because this goes to infinity, and so it is 0. There we go. If it were the other way around, we would have done the same thing, but instead it would have been infinity over 2, and we would conclude
It doesn't exist.
it doesn't exist, right? Or that it blows up, it goes to infinity. Okay? Okay, now, the question you're asking about. So, by the way, these types of limits are called indeterminate. Okay? And I don't think that they called it, did they call it here? Yeah, no, they were indeterminate forms of type 0 over 0 or of type infinity over infinity. Now we're going to talk about indeterminate forms of type zero times infinity, or infinity times zero, right? It doesn't matter which one's which, right? But if you have this type of thing, and it's going here, let's take a look at an example. But the idea is who wins? Who's going to zero faster and who's going to infinity faster? So here's an example. This is from your book. This is number 46. We have the limit as x goes to infinity of x times tangent 1 over x. So we could see that this goes to what? What does that guy go to?
Infinity.
Infinity. And
Tangent
then
of 0 is
that
just
would
0.
be tan, so he's getting closer and closer to tan of 0, which is
Just 0.
just 0. So we are in this form, right? We have a indeterminate limit. Now we want to ask who gets there faster. The cool thing about this is anytime you have infinity times 0 or 0 times infinity, you could just rewrite this as a quotient. Watch. I'm going to say, and I could do it either way. I could put one guy in the numerator, one guy in the denominator. The easier one to keep in the numerator is going to be this guy. Now I'm just going to rewrite this as 1 over x down here. Now what's this going to?
0 over 0.
Ah! So anytime you have an infinity times 0, you can rewrite it as either going to 0 over 0, or if I had done it the other way, I could have kept x in the numerator and then just put this guy down here.
Oh, okay.
Isn't he exactly the same thing? Isn't this exactly the same thing as that?
Yeah.
Which is exactly the same thing as that. But now he would be going to infinity over infinity. But the question is, now you know what we're about to do, because this is all about L'Hopital's rule. Which one of these is going to be easier to deal with?
0 over 0.
I think that one's going to be easy because that, I mean, I guess you could call that cotangent. But I don't remember what the derivative of cotangent is, so
Does anyone remember?
Right, exactly, right? I've already jettisoned that information. So, okay, so this goes to 0 over 0, so I can apply L'Hopital's rule and say that this is the same thing as the limit of their derivatives. So what's the derivative of the top? Derivative of tangent is
Secant squared of 1 over x.
secant squared of 1 over x.
x negative 1 over x.
Yeah, right, because that's x to the negative 1. You take the derivative, the negative 1 drops down. You bring that down to a negative 2. That's negative 1 over x squared. Negative 1 over x squared. What's the derivative of that?
Negative 1 over x squared.
Right, it happens to be the same thing. Can you see any cool cancellations we could do?
Let's see one.
Because if you don't do that, you're going to say, okay, now let's take the limit. This guy goes to secant squared of 0. That's so that goes to 0. Secant squared of 0 is 1. That goes to, oh, I'm sorry, yeah, infinity, right? Yeah. So then that goes to 0. He also goes to 0. So we still have 0 over 0.
Yeah.
Okay, take the derivative, L'Hopital's rule, and then you just, it's going to get horrible, right? So use your brain every time. Every time you apply L'Hopital's rule, stop. Say, can I make this easier on myself? These happen to cancel out. Nice. So I could say this is the same thing as the limit as x goes to infinity of just plain old secant squared 1 over x, which is what?
Secant squared of 0.
Secant squared of 0, which is?
1, I think.
I think it's 1, because this is the same thing as 1 over cosine squared 0,
Yeah.
which is 1. So 1 over 1 is indeed 1. And so, infinity times 0, in this case, happens to be 1. Because I guess they're both going in their directions at the same rate. X is going off to infinity at the same rate that this guy is going to 0 or something. I don't know. I mean, that's kind of what this means, right? The limit of the ratios, they're going at the same speed.
Yeah.
And so it works out that it balances out to 1. But it could have been 0. It could have been infinity. It could have been negative infinity, right? There's a lot of different ways that this could go. And it depends on how fast you're going. So, you guys like that? I mean, that's pretty much what you do. Anytime you get a limit that goes to 0 times infinity, you just rearrange it, because you could always rearrange it as a quotient that's going to both infinities or both going to zeros. And then just apply L'Hopital's rule. All right, so now, so that was called an indeterminate product. Now we have indeterminate difference. If you have a limit of something, and this is, by the way, like that, not the limit of f of x, and then you minus off some g of x. This is the limit of this goes to infinity minus infinity. Now note, this is tricky, because 0 minus infinity is just minus infinity. Infinity minus 0 is just infinity. That's not indeterminate. That's just what it is. This is like, well, they're both going to infinity. So at what rate? At what rate are they going to infinity? It might work out that it could be infinity, it could be negative infinity, it could be 0, it could be any number in between. So but it's only if they're going to infinity minus infinity. And by the way, not minus infinity minus infinity. That's not indeterminate. That's just going to minus infinity.
Yeah.
So you gotta be careful with this one. It's only positive infinity minus infinity. If you have some limit that does that, then you're in a world of hurt. These just suck. These really suck. And like I did one earlier, and I just kept getting the same thing over and over and over, and it was terrible. What?
Wait, never mind.
Yeah, no, and that's the problem. Is like, you know, the limit. You could say, well, that's the same as the limit of f minus the limit of g, but then you still get infinity minus infinity. And so, what you hope to do. And your book doesn't give you any clues about like what to do if this is not obvious. But it says, for instance, if we have this is number 48, minus cotan. First thing we do is we just plug it in. What is cosecant 0?
Yeah, infinity. Cause it's like
Yeah, it's infinity, because sine does this, and at 0, so dividing by it would give you that. What about cotangent at 0?
Also infinity.
Also infinity, because tangent goes like that. Cotangent's 1 over that, so he would also go to infinity. And I think, did it do that? It didn't. I'm not sure if it gave us as we go from the right or not. I don't know if I copied it down right, who cares? What you do is, in a case like this, your book just says find a common denominator. They're both over sine. Okay, so let's just rewrite this. Anytime you have trig functions, like no matter what you're doing, it's probably a good idea to write them in terms of just sine and cosine, and then see what happens. And in this case, now we can rewrite this as the limit as x goes to 0 of 1 minus cosine x over sine x. Now what do we have? What does this go to?
0 over 0.
0 over 0. We have to check that, because I mean you're thinking L'Hopital. Oh, use L'Hopital's rule. Can you? Wait a second, because if this were just cosine over sine as it goes to 0, well, that goes to 1. That goes to 0. Oh, that's just infinity. You can't use L'Hopital's rule, but this time you can, because they're both going to 0. So I'm going to use L'Hopital's rule to get that this is the same thing as the limit as x goes to 0 of, what's the derivative of the top?
Just negative sine of x.
Negative?
Oh wait, positive because it's negative.
Yeah, right. Right, yeah. So positive sine over
Cosine.
cosine. And now we could just plug it in. And we get sine 0 is 0 over cosine 0 is 1. This just works out to 0. So I guess they're going to, I guess you could say, then they're both going to infinity at the same rate if this difference works out to 0.
Okay, yeah.
These guys are going at a different rate, but these guys here, back here, they're both going to infinity at the same rate. So when they get big enough, then they're about the same magnitude, so they subtract off to 0. Okay. Your book gives you no hint on what to do with this. And it's so annoying. And you'll see, this is an odd number that I did not assign. Because, oh man, this is number 49. And it's the limit as x goes to infinity of root x squared minus x minus x. What does this go to?
Infinity minus infinity.
Infinity minus infinity. And if you happen to
Well,
have...
infinity squared minus infinity.
Well, it's not infinity
And that's
squared,
the
because
root.
infinity squared is infinity.
But then that's infinity minus infinity root minus another infinity.
Yeah, well, yeah, but x squared is a much bigger infinity. Like what? This is just some function.
Oh, wait.
This is just some function,
Yeah.
and it happens to look like this.
Oh.
Well, it actually happens to go through right here, but whatever. And as it goes to infinity, this guy goes to infinity.
Yeah. Okay.
And so ditto does its root.
Yeah.
But that happens to flatten it out a bit. That guy also goes to infinity. And so it's like, well, which one is going faster, really, is the question. And all your book has ever said to this point is try to find a common denominator. That's the only help your book gives you. Try to find a common denominator. And so if you're like me, you're like, well, well, we could do something like this, right? Because I see a root minus something,
Out of the
and so I think, well,
conjugate?
yeah, right? That's what you think to do, right? You do this, right? And you go, and it never ends. And you just apply L'Hopital's rule forever, and it never ends. You just get the same thing over, and you eventually end up in this situation. Limit as x goes to infinity. After about 1,000 applications of L'Hopital's rule, you end up with this. Oops. That was the actual answer. You end up with something that looks like this. 2 root x squared minus x over 2x minus 1. And so you apply L'Hopital's rule again, and you get the thing that you got before, which is like, and because you do a bunch of cancellations, and you end up with 2x minus 1 over 2 root x squared minus 1. So you do L'Hopital's rule again, and you end up here, and then you go here, and it's so annoying. And you're like, well, I tried to find a common denominator the way that you told me to, and there is no common denominator, and so then you gotta get creative. And this is why I didn't assign this one. I didn't assign anything that's like this, but I just want you to see this because there's actually something cool here. So you say, okay, I'm gonna get creative. This goes to infinity. What happens if I factor out an x squared here? X squared, we get 1 minus 1 over x right there, minus x. Now that x squared comes out as an x. X goes to infinity, comes out as an x, and we get 1 minus 1 over x minus x. And now I have an x in both of these, so I can pull it out. Limit as x goes to infinity of x times root 1 minus 1 over x minus 1. Now what does that go to? Product.
Infinity 1 minus 0. Or just 1, 0.
Yeah, so this goes to infinity times 0. Okay, now I'm going to do the trick. I'm going to take one of them into the denominator. So that's equal to... Now, which one of those in the product would you like to take into the denominator?
The x.
The x, right? So I'm going to write that as 1 over x.
Yeah.
And then the numerator stays like this. Now we have what? This goes to what over what?
Infinity over 0. No, sorry, 0 over 2.
Yeah, Okay, so now we can apply L'Hopital's rule, right? Okay, L'Hopital's rule tells us then x goes to here. Okay, the derivative of square root of something is 1 over 2 times that something.
Times the inside.
Times the derivative of the inside stuff. So what's the derivative of that?
1 over x squared, yeah.
Positive 1 over x squared. Okay, so all of that times 1 over x squared. Now, what about the bottom?
-1.
Negative 1 over x squared. Negative 1 over x squared. Now, if you're not paying attention, you evaluate this, you're like, it's still going to 0 over 0. Oh no!
Negative
Or
cancel.
cancel it. And we get limit x goes to infinity. There's a negative there.
So -1 over -1 onto. Okay. Can you pull out the negative? So you're not supposed to be.
No, there's supposed to be a negative. I did it wrong. So, yeah, the negative, we'll just call it negative 1 over 2, 1 minus 1 over x. Now, can we do that?
Yes.
Yeah.
So that's
That guy just goes to 0.
So it's 1, which is 2 times root 1, so -1/2.
There, 1/2. Infinity minus infinity equals -1/2.
Interesting.
Yeah, interesting, huh?
So the second infinity is
So there's
1/2
no real
bigger
answer.
than
I guess. It shouldn't be a negative. I swear I checked this in the back of the book because it's an odd problem. I don't know. I don't know what happened here. I think I could see where I didn't take that negative into account and why I got positive 1/2. Who cares? Okay, I hate these. Those are no fun at all. So, okay, there's one last kind of indeterminate form that we want to talk about. And it's where you have the limit as x goes to infinity of f of x raised to g to the x. So this is a indeterminate power. You have some function raised to some power, and it goes to, and this is, you got to be careful about this because there's only 3 kinds of things that make this, where you could do this. It goes to 0 over 0, or it goes to 1 to the infinity, or it goes to infinity to the 0.
the 0 is just 1.
Yeah, well, we don't know. It's indeterminate.
Oh.
This is like, it depends on how fast they're going. And like, so for instance, like infinity to the 1, there's no problem there. That's just infinity. Infinity,
Wait, 1 to the infinity is indeterminate? 1 times 1 times 1 times 1 forever?
Yeah, that should
but
just be
look at,
one.
okay, well let's look at, here you go. Here's the limit. So what, so okay, here's my question. You have the limit of some function. And it is going to, that's not equal, but it's going to 1 to the infinity. Your guess is that this equals what?
1.
1.
Probably wrong.
Okay, well let's see. I'm going to come up with something.
Okay.
That goes to
Yeah.
1 raised to the infinity. Is that limit equal to 1?
As x goes to where? To what? To 0.
Wait, where's x going?
Oh, I'm sorry.
Yeah. So,
So you just told me if it's 1 to the infinity, it should go to 1. What is that?
1 to the infinity.
Okay, so it goes to 1 to the infinity, and I'm telling you that's indeterminate. You should recognize this limit.
Oh.
You might recognize it if I replace it. Yeah, 1 in. So you see why I mean it's indeterminate. You can't just say, oh, it's 1. Well, hold up. Something's going on here. It depends how fast this guy's going down to 1 and how fast that guy is going to infinity. If he takes forever now this guy goes down to 1 pretty fast, but if he takes forever to get down to 1, then he might blow up for all we know. We don't know. It's indeterminate. And
if there was no limit and you just multiplied 1 by itself infinitely, wouldn't it still be 1?
It would just be 1. Yeah. So if you just took 1 and raised it to the whatever that means, right? Or so, for instance, the limit as x goes to infinity of 1 raised to the x would just be 1.
Yeah. Okay.
Yes, but we're talking about where you have a function going to 1 and a function going to, and that's the trick. And so what do? Well, this nifty, we know what we had to do for this guy, but I wanted to prove that this goes to e. I wanted to be rigorous, right? I wanted to show that this number actually exists. What you do, though, to make this a lot easier, is so we'll come back to him in a second. What you do is this. You have some function raised to some power. And what you do is say, this is exactly the same thing as e to the log of that stuff. Yeah. Almost. Now, we're going to pull, right, this is why I mean, I could have chosen I could have said, that's the same thing as f to the g squared square root. But it doesn't help, right? So I'm choosing to take this way because it's going to help me, because log has that nifty property that this happens. Now let's just look at this. If log goes to if f, right, because we're seeing f is going to 0. If f goes to 0, then log is going to negative infinity.
Yeah.
And so negative infinity, g can go, if the only hope is that this guy goes to 0. And that would be that guy right there. Right? Log, or the f going to infinity.
Yeah.
The f, oh no, wait.
It would be like 1 to the infinity. E to the infinity.
Yeah, and the g is going to 0. You see what I'm saying here? It'll become clear in a second. You basically, like, this is what you need to remember. Just look at your thing, do this. It's going to work every time. But then what do? Well, this is what I'm telling you here. So this is the same thing as this. Yeah, they mean exactly the same thing.
Yes.
As long as f is positive.
The function.
Because can you plug it? Yeah.
Oh.
Because can you do this? What's log of negative 2?
Yeah.
It actually works. You could do it with complex numbers. It turns out you can put in negative numbers into log, and this still works. So, but the limit as x goes to, this should have been a, it could be anything, is the same as this. But if that's the case, then what you do is you evaluate the limit here.
Because it doesn't really matter.
Right, because e's not changing as you change x. So you just evaluate this limit. You just evaluate that limit. And then when you're done evaluating it, you plug it into e. You see what I'm saying?
Yeah.
Because
kind of like a
This,
substitute.
this is this, and if you're changing x, then okay, it changes this stuff, but e is just e. He's not changing. So you could do the evaluation in here. You see what I'm saying?
It's kind of like a substitution.
It's kind of like a substitution, yeah.
Yeah.
You just got to remember that you're doing all of this in e.
Okay.
So let's do this one here. Okay. And I don't remember that as a formula. I remember this as a method. I see, okay, I have one, this, as x goes to infinity, this goes to 1 to the infinity. Is that one of these three? Yes. And so this should work. I'm going to say this is the same thing as the limit as x goes to infinity. Oh, I have a power. I could undo the power by doing this.
Yeah.
Now I have 1 plus 1 over x raised to the x. So this is the same thing as the limit as x goes to infinity of e to the x log 1 over x. And so I'll come back, I'll figure out what this is, then I'll come back and plug it into e. Okay? So what is the limit as x goes to infinity of x log 1 plus 1 over x?
It's infinity times 0.
Infinity times 0. So
Yeah, we can work with
we could do the thing.
the hospital.
Which one? Well,
Wait, no,
we're not
no.
quite. We're not
You have
ready
to
for a
make it
hospital yet.
Common denominator.
Oh yeah.
Yeah, we need to split this guy up because we're not quite there yet. So who do you want to leave in the top?
The log.
Log. Okay. It would work if we did it the other way, but I think that's the wise way to do it. This is exactly the same thing. That has not changed, has it? I just rewrote it.
Yeah.
It's exactly the same thing. I just like to make that note. Now, as x goes to infinity, this guy goes to 0, we get log 1 is 0. As this goes to infinity,
Over
we
zero.
get 0 over 0. So we can use L'Hopital's rule. Hold on.
1
It's what?
over
1 over all that
1 plus
stuff.
x times negative 1 over x squared.
Negative 1 over x squared. And what's the derivative of the bottom?
Negative 1 over x squared.
And this
So you can cancel.
We can cancel, right? Don't. Oh, it's still going to 0 over 0. Oh, what do I do? No, we could cancel. Now, it just so happens that the ones that I chose, I didn't realize this until a few minutes before you got here, that everyone I did, they happen to cancel. Sometimes they won't cancel exactly. You might have a cubed up here and a squared down here, and they'll cancel a little. Exactly. You want to combine them and rearrange it so that it works well.
Yeah.
These just happen to cancel, and we get, okay, the limit as x goes to infinity of 1 over 1 plus 1 over x. And what's that?
1.
Yeah, because as this goes to infinity, that guy goes to 0. It's the same thing as 1 over 1, which is 1. But we're not done.
Yeah, it's e to the 1.
It's e to the 1. And what's e to the 1?
Just e.
So...
Wait, but what if you had used a different base of log? Like, then you would have found that
Oh.
it equals.
Well, then when you take the derivative, some other stuff would have popped up.
Oh, yeah.
Yeah. So you could have done that. Like, we could have said this is the same thing as 2 to the log base 2 of 1 plus 1 over x raised to the x. And then, but then how do we take the derivatives of those things?
Turn
We
it back
turn it back into e.
Yeah.
Because e's the only one we know. Now, you see why I didn't, like, I wanted to show that this thing exists, and so we did 4 hours of lecture showing that this limit does in fact exist, because you know, if I want to prove that this thing exists, I'm not going to say we can use L'Hopital's rule. E to this is that. It's like, well, you don't even know that exists. You can't just start with it.
Assumed it exists, prove it exists.
Exactly. Then you got this circular thing. Well, it exists because of L'Hopital's rule, but you used this, you used it, and so you had to have it exist before, yeah, but it exists because of L'Hopital's rule. It doesn't work. Okay, so there's that. Yeah, finally, one more example. So, does this make sense?
Yes.
right? And I don't think about it as like that this limit, like what I don't have in my head is this. I do not have this in my head, but this is the same thing as the limit x goes to a of e to the log of f, and then you bring down your g. I don't think about it that way. I just think, well, hold up, I have powers. It's doing something funky. And so, and then I just go and apply this. It's not that I've memorized this, you know what I'm saying?
Yeah.
Okay, because really, anytime there's something funky going on with powers, the thing that we almost always do is this trick, right? Just like it's like, I need to take the derivative of 2 to the x. So what do? Well, I rewrite this as this.
Yeah.
And so that's the same thing as this, x log 2. And so when I take the derivative of it, I get e to the x log 2 times the derivative of the inside stuff, which is just log 2. Log 2 comes out. And so this is just log 2 times, well, I guess 2 to the x.
Yeah.
Right? So that's...
What do you even call it? It's not raising it, you're like lowering it to the e.
I don't know, right? So, okay, again, I don't want to forget, this is works for 0 to 0, or 1 to the infinity, or infinity to the 0. Okay, so let's look at this one. The limit as x drops down to 0, approaches 0 from the right, of x to the x. Now,
So
0 to the 0. So we,
okay, so this goes to 0 to the 0. So it's one of our indeterminate forms. It could be anything for all we know.
yeah.
It might be e. It might be -1/2. Like, we don't know. This is what this means, indeterminate. We don't know.
So do this e thing.
So we're going to do the e thing. I'm going to say, okay, the e thing. So let me just rewrite this thing. So I'm not changing anything. We're doing this. I'm going to rewrite this as e to the log of the stuff. That stuff is x to the x. But instead of writing my x right here, I'm going to go ahead and drop them down to here. Okay. Now, I'm going to look at this and say, okay, e doesn't change. So really what I'm looking at is the behavior of this function as x
which is 0.
goes to 0 from the right. And now you see why the book said from the right. Because if you tried to plug in a negative number there, yikes. What you would do, I'm just telling you, we're not going to do this in this class, but you would rewrite this as this. And then you bring your x down. This is the complex logarithm. Complex logarithm can take on you could put negative values into it. Why?
Wait, is
Well,
it base I or?
Base EI
so
or something.
remember that every complex number z can be written as r e to the I theta.
Yeah.
And so every complex number has a
And then you can take out the
log. Complex log has the same properties as real log,
and you can drop down the I theta.
and then the I theta just comes out because this is the undo e. We're going to undo e to the stuff. This works out to just be plain old log of r plus I theta. And so, yeah, you get an I pops out. Now you have a complex number. That's how it works.
So the complex log works the same as a natural log unless it's negative numbers. Like if you plug a positive number into natural log, into the complex log, it does the same thing.
Yes.
Yeah.
Yes.
Yeah.
If you plug in, so for instance,
1.
how about 2? Then this is the same thing as 2, but your theta is a 0.
Oh, yeah.
And so then this just works out to be a big fat 0.
Yeah,
So it's
log
just
2.
plain old log. Oh, and I should have done this. Natural log. Because if that's a positive, r is always a positive real number.
Yeah.
Right. And so, okay. And if it's -2, then r is still 2.
Yeah.
R is still 2. But now theta is pi. Right? Because e to the I pi equals -1. And so -2 equals e to the I pi times 2, which is this. And so you undo it with that, and now it's just this.
Yeah.
So there's no problem. We can still do this if you had negative numbers. I just want you to know that. It's possible. It's just that an I pops out with some radian value. Yeah, interesting. So, okay, anyway. So, what do we have here? This goes to what?
0 times 0. No. Wait.
0 times
Times
negative infinity. And remember, as you're doing this, negative, positive, who cares? If it's infinity, it's infinity.
Unless
right?
it's the plus one.
Yeah, we don't care. We don't care what it does.
So
uh-oh.
take it as denominator.
Which one do you want to take into the denominator?
X.
You know what? We've been doing that a lot. I'm doing this on the fly. I haven't done this before. Let's do it the other way around. Well, let's just see what happens. And I'm going to go 1 over log x. Is that the same thing?
Yes.
I haven't changed anything. I wrote it a little bit differently, but now this goes to what over what?
1 over
1.
1, 0.
x over 1. X. No,
X
0.
goes to
0.
Uh-huh.
It's just 0.
and
Over
then
is 0.
over 0. Okay, so can we use L'Hopital's rule?
Yes.
Yeah. Okay. L'Hopital's rule. So this is why you don't want to take the harder one into the denominator, but we will. So x goes 0 from the top. What's the derivative of the top?
1.
Okay, now the bottom is this. Natural log of x to the -1. Take the derivative.
-1.
Yep,
log
the
of x to
-1 natural
times
log of x to the -2 times
1 over x.
1 over x. So that could be rewritten as negative 1 over x
log x squared.
log x squared negative 1 over x log x squared. Oh boy.
You can flip it.
Yeah, you can flip it, and I can see that now I'm going to be back kind of in this situation, when it's going to be negative, and then that's squared. I just made my life harder.
So that's why you
So that's probably why you don't want to do. Now you could. But if you do something like this, and it gets harder than the thing you started with. Actually, I don't want to say it. Don't, because sometimes it looks harder, but it turns out to be easy. But as we can see, this would be the same thing as the limit of negative x log x squared. And now we can see as it goes to 0, we get 0, negative infinity, squared is infinity. So, okay, 0 times infinity, and we're back where we started. In this case, I'm going to say, once we get to here, we go, ooh, that made my life harder. Let's redo it. Let's just do it this way. Log x over 1 over x. Now, that goes to what over what?
negative
1 over
infinity
no.
over 0.
Over 0.
Oh wait, over
Wait,
what?
yeah, negative infinity over infinity.
Aha. Right, because as it's going to 0, 1 over 0 goes to infinity. So we have an infinity over infinity. So we can use L'Hopital's rule. Careful, because they will try to trick you. They'll give you something and you'll just do it and think, oh yeah, L'Hopital's rule. But it might be that L'Hopital's rule doesn't apply. And so then, well, I don't know, whatever. So by L'Hopital's rule, we get, I mean, it would depend. You'd have to figure that out. But we saw when L'Hopital's rule doesn't apply, you know, like you get infinity over 0, oh, that's just infinity. Or 0 over infinity, oh, that's just 0. So that's kind of one of those situations. So, okay, but L'Hopital's rule does apply. What do we get on the top?
1 over x over negative 1 over x squared.
Negative 1
Cancel
over
1
x squared.
x's.
Yeah, I'm going to rewrite this.
It's just 1 over 1 over
Yeah.
Which is
I'm
just
gonna go
x.
1 over x
Just
times negative x squared over 1.
Yeah.
And now I get limit as x goes to 0 from above, negative x, which is what? Which is just 0. And so now I say that this is the same thing as e, because that's the limit we
right.
took right there. Yeah, you gotta be
0,
careful.
which is 1.
See, this is the thing. You're gonna do this, and you're gonna go, it's 0. I'm done. No, that's not what you're doing. I mean, that's why it might. I mean, I would not want to do this every time, but that is what you're doing. It's finally the limit of this stuff. This goes to 0, so it's e to the 0, and e to the 0 is
1.
So you could argue that 0 to the 0 equals 1, but not in every case, right? It's not always going to work out this way. Like, you're going to have in your homework that guy. And so when you say, well, what's 0 to the 0? Well, you might get something different.
You probably will.
You probably will. And so it depends. It depends. So, you know, I've been asked a bunch of times, especially when we were doing algebra 2, what's 0 to the 0? Well,
If you have 0 to the 0 equals 1, and you take natural log of both sides, then it'd be 0
yeah, 0 to the 0 equals 1. And so you take the log of both sides, and you get 0 times log 0 equals log of 1 is 0.
So 0 times negative infinity. is
Oh.
So 0 times negative infinity, also indeterminate.
Yeah.
It depends. How fast are you? And you see, this is the thing. Is like, how fast are you going there? Is he going there at a rate? Are they going there at the same rate? Which would be this case. That's what you're doing there, right?
Yeah.
And so you could say that, but it's like, well, first off, what does that mean? It doesn't. Like, you're starting off with something that it doesn't mean something. Like, what is this? How did you get there? Did you just take 0 and raise it to the 0? What do you mean by that? You know, so this is what it means by
What does
indeterminate.
anything raised to the 0 really mean?
Or,
It's like-
yeah, I mean,
Yeah.
and so
Five times itself is
it
0.
depends how fast you're going. And that's what L'Hopital's rule is all about. It allows us to compare how fast things are going somewhere, right? And that's what it says. That's what it says the answer is, right? It said that the limit as x goes to 0 of x log x. It's like, well, they're doing something weird. You can rewrite this as this right here. They're both going to infinity. How fast are they going to infinity? Right? That's the question here. And so 0 to the 0 is like, well, you're going, it depends, right? Are they going at the same rate? And if they are, then you happen to get 1. If they're both going to 0 at the same rate. So you have, for instance, the sequence 1 to the 1. And then you have 0.5 to the 0.5. And then you have 0.1 to the 0.1. And you just compute this sequence, you'll see that this sequence will approach 1. Right? But we're doing it at the same rate, right?
Yeah.
1 and 1, 0.5 and 0.5, 0.1 and 0.1. Eventually we get down to 0.01 raised to the 0.01. And all of these values will go to 1. But it's not necessarily going to be the same as if we do it x squared.
Like x to
You get
2x.
1, 1, and then 0.25, and then 0.01, and then this guy would be 0.1, 2, 3, maybe 4, I don't know, ones, right? And then what's that sequence going to go to? I don't know. You'll find out when you do this in your homework.
Pretty less than 1.
Maybe.
Probably. Notice that. I don't know.
It might be 0. I don't know. I mean, I'm sure I've done this before, but I did not attempt that one. But I'll tell you how you do it. I'm curious now. I gotta know. You guys want to find out? You know, I want to find out. I gotta know. So, okay, let's see. This is the same thing as the limit as x goes to 0 from above of e to the log x. The x squared drops down.
So then
Now we say, okay, so that's the same thing as the limit as x goes to 0 from above of x squared log x. this goes to 0 times negative infinity. Ah, so it's indeterminate. So we can rewrite it as x goes to 0 from above of, which one do you want to put in the denominator?
X squared.
Yeah.
Over X.
Yeah, let's do that. So log 1 over x squared, or how about x to the negative 2?
Oh yeah. That's,
I mean, yeah, it is 1 over x squared.
Yeah.
But it's going to be easier to take a derivative if we do it that way. So let's do that. We say, okay, whoa, actually, we're not ready yet. Because this goes to infinity. And what does that guy go to as x goes to 0? Also infinity. So we have infinity over infinity. So we can use L'Hopital's rule.
wait. Oh yeah. Sorry.
Right, the negative. I know. I keep looking at that and going, we can't use L'Hopital's rule. But yeah, it's the way we've rewritten it. Okay, so the top gives us what?
1 over X over negative 2x to the
Negative 2 x to the negative 3. Or negative 2 over x cubed. So negative 2 over x cubed. Now, oh, it still goes to infinity over infinity. No! Just chill out for a second and see if you could rearrange it. This is the same thing as limit. Because you could just keep using L'Hopital's rule, by the way, right? But you don't want to do that. We're going to say that's 1 over x.
So it's
This is the same thing as x cubed over negative 2.
It's just x squared.
Yep. Limit as x goes to 0 from above of x squared over negative 2. What's that? It is 0. Okay, so it did go to 0. Huh, interesting. I just realized I did the thing I told you not to do. Here I said, oh, so the limit is 0. I did the very thing that I said, make sure you don't do this. I said, therefore it goes to 0. Is that true? No. We were evaluating this part of this. So what I should have done is said, okay, so the limit of e to this stuff as x goes to 0 is the same thing as the limit of this stuff going to 0, which we found was 0. And then I plug that back in there at the end. And so yes, it does go to 1, not 0. Be very careful, because as you can see, you're going to completely lose track of what you're doing when you get down to here and say, oh, that's the answer. It's not the answer. You got to go plug it back in to E.